So it is my pleasure now to introduce our second speaker, Abhishek Sambyal, who has a PhD in computer science and engineering from IIT Ropar in India and is currently a postdoc at the University of Hulu. And his research focuses on uncertainty quantification, confidence calibration, which we are realizing more and more now is an important metric to measure, and improving the reliability of deep learning in medical imaging. So, Abhishek, you have the floor.
Thank you, Veronica. I think you can, I hope you can see my screen.
Yeah, all good.
Yes. Yeah. First of all, I would like to thank Veronica and others for inviting me for this talk and let me share my research, one of my research books with you all. So let's get started. So I'm Abhishek Singh Sambyal. I've done my PhD from IIT Roper as Veronica explained, and currently I'm doing postdoc. Currently, I'm a postdoctoral researcher at Intelligent Medical Systems Research Group at the University of Oulu. Today, I'll discuss one of my research works on understanding calibration in medical image classification. So, as we know, deep learning is everywhere, be it healthcare, autonomous driving, weather forecasting, you name it, and it's all because of its performance. But performance-based decision making can sometimes lead to unsuitable outcomes, especially in safety critical applications like healthcare. Why? Because performance does not capture the untrustworthiness. And because of that, its adoption in healthcare, especially in decision making, is very risky. And we have seen a lot in the news that AI is not trustworthy enough. They are black box algorithms. They are biased towards some ethnic groups, etc. And all these issues they affect its adoption in the real world. So the question is how to build trust in deep neural networks. The answer to that is trustworthy deep learning. It provides reliable, robust, transparent, and fair models that help us take better decisions. This is an umbrella of trustworthy deep learning where, just a second. This is an umbrella of trustworthy deep learning where we have multiple facets like robustness, out of distribution generalization, uncertainty, explainability, and bias and fairness. So, in today's talk, I'll discuss more about the uncertainty, and especially I'll look into the calibration aspect of uncertainties. Just a brief about it. So, what are the sources of uncertainty? They are basically two. One is aleatoric uncertainty. It is the uncertainty in the predictions that is caused due to the noise in the input data. Second is epistemic. We call it model uncertainty. It's the uncertainty in the predictions due to the lack of knowledge of the neural network. There's another one, what I call it as an interpretation of uncertainty is the confidence calibration. It measures the disparity between the model's accuracy and the predicted confidence. These plots, what you can see, they are called reliability plots. They tell you how much miscalibration is there in the model predictions. So on the left, you have LayNet, and you can see there are less gaps, the red blocks, which means the miscalibration is less. Whereas this ResNet, which is a modern neural network, it suffers from huge miscalibration, and the type of miscalibration is overconfidence. So the question is, what causes miscalibration? Overfitting is the cause of miscalibration, and there are a lot of factors that affect the overfitting, which is like large model capacity, batch normalization, less weight decay, etc. The negative impact the calibration of the model. Let's look into the example of calibration and see how can we measure it. Let's suppose you have 9 samples and we have maximum estimated probabilities of those samples, predicted label, and true label. On the right side, we have 5 different bins. They are of fixed sizes and they range from 0 to 2. Every range is of 0.2. What we'll do, we'll assign every sample their respective bin based on their maximum probability or confidence values. After we assign the samples, for each bin, we'll first calculate the accuracy of that bin, and then we'll estimate the or calculate the average confidence of that bin, we'll take the average difference, or sorry, absolute difference, and then we average all the absolute differences of all the bins. The value which we get is called expected calibration error. And the higher the value, the more miscalibrated will be the model predictions. So our goal in calibration is that we want to reduce this gap between accuracy and the confidence so that the model predictions can be trusted. Let's see some of the existing literature and motivation for this study. One of the concepts is transfer learning. This paper, Transfusion, it talked about how learning from natural images can be translated into medical images. Because before that, not much has been explored. So this paper talked about the transfer of the transfer of learning from from natural to medical images. They found out that the transfer learning offers very limited performance gain when we use ImageNet pre-trained models. And also, simple and lightweight models, they were performing very comparatively better compared to ImageNet architectures, those were big. The main focus of this study was on evaluating the performance when we are doing the transfer. Few other works like pre-training and self-supervised learning, how they are good for model robustness and uncertainty. So if you see this plot on the left, this is the performance plot on CIFAR 10. The blue ones are the inputs where the noise has been induced, like Gaussian noise, brightness, saturation, etc. And they found out that pre-training and self-supervision, they both improve model robustness in terms of performance. And they were evaluating on performance metrics like accuracy, test error, AUC, ROC. And one more thing, these studies were done on natural image dataset like CIFAR 10, CIFAR 100, ImageNet. The question is, and the problem is, the observations what we make on natural images cannot be corroborated on the medical images due to varied nature of data. And also, this work was not focused on calibration and more focused on performance. There are other methods which have been used for improving the calibration, not understanding much, but improving it, like Platt scaling, temperature scaling. These are called post hoc approaches, which are used when whole training is over. There are other approaches like train time calibration, which directly generates calibrated DNN models, and they are done during the training process, during the training optimization process, like entropy-based regularization, label smoothing, focal loss, they all help improve the calibration of the model. So what was the research gap? Focus of the existing literature was on natural images. They were comparing only performance, and understanding calibration was not emphasized. What was missing? Understanding calibration and medical imaging, impact of data sizes and model capacities on calibration, impact of training regimes and pre-training strategies, what aspects of DNN that contribute to the calibration of the model. But the question is, why do we need to have this study? One is computer vision versus medical imaging datasets. Whatever we understand about the computer vision datasets cannot be directly applied to medical imaging datasets because of the different nature of data. And also, in medical imaging, we have dataset scarcity. So it's very difficult to um, translate whatever we understood about the CV dataset into the medical imaging. Because we have smaller datasets in medical imaging, the transfer learning approach becomes the de facto approach. Therefore, we need to understand how transfer learning affects the model calibration. Next, we want to compare how self-supervised learning approaches versus the self-supervised learning approaches affect the model calibration, because self-supervised training has become a new paradigm for training newer models. So our problem statement is to explore the calibration of medical image classification systems. And with that, we wanted to see the effect of different training regimes with or without transfer learning. And in this training regimes, we have used three. One is fully supervised with the random initialized model, fully supervised with pre-trained model. So today I'm only going to discuss the ImageNet pre-training, not the RAD ImageNet, and the self-supervised learning, where today I'm going to discuss the rotation-based SSL. So we want to compare these training regimes And we want to see what is the effect of dataset size and architecture size on the calibration. Also, we wanted to see that what are the potential factors that affect the performance and calibration. So just a brief about training regimes. As I told you, I use training from scratch. I call it FSR. It will be shown in the results and other slides. Image pre-trained models, we call it FSP, P for pre-trained, and self-supervised learning, SSLP, P for pre-trained. So in this self-supervised learning task, we have used two heads. One is the classifier module, and another one is the auxiliary module. So this act as a self-supervised setup. Here, the auxiliary module is a rotation-based SSL where the model is predicting the induced rotation in the input. For our experimental setup, we have used three different data sets: diabetic retinopathy, histopathology cancer, and COVID-19. And we have segregated these data sets into 500, 1,000, 5,000, and 10,000 dataset sizes. We have also used different dataset architectures from small to large, ResNet 18 to wide ResNets, and two performance metrics and six calibration metrics. Let's look into some of the results. So these are the plots. These plots shows the joint evaluation of performance and calibration of wide ResNet architecture on diabetic retinopathy dataset. First two plots are the performance plots. Next six plots are the calibration plots. And x-axis represents the different dataset sizes, and y-axis represents the metric name. So if we see first two plots, which are the performance plots, we see the performance, the pre-training improves the performance over the random initialized model. As you can see here, this blue is the SSL and SP is the red one, and the orange one is the random initialized. We can see there is a significant improvement in the performance if we use a pre-trained model. If we compare pre-training like FSP and FSR, we see that the calibration is better for smaller data sets. If we compare the training regimes like SSLP and FSP, we see that self-supervised learning approach is better in terms of calibration throughout all the data set, all the metrics, calibration metrics. And the same trend has been seen for histopathology dataset as well. As I showed you the results, I have used six calibration metrics, but the question is, why do I need six calibration metrics? Why can't I use just two or just one? So let's see what is the issue using a single calibration metric. So each of the subplots are the metrics. So I just urge you to focus on the second column, which is ECE. This is one of the calibration metrics where we evaluate what is the calibration error. The same color coding has been used. The red one is FSP and the blue one is SSLP. So I just wanted to name the color rather than FSP and SSLP for easier understanding. So here we can see the blue one is better for smaller architecture, and the red one is better for the larger architectures, which shows that FSP is better calibrated than SSLP for smaller models, and for larger models, and FSP is better for smaller models if I only use ECE. But if I use ACE rather than ECE, the trend becomes opposite. So now if I had used only one of the metrics, I have reached to the wrong conclusion. So we suggest that rather than using one single metric or just two metrics, we should use multiple metrics and then evaluate or then use those multiple metrics for model selection. But the question is, if we have if we have different results for different metrics, how can we do the model selection because of the mixed calibration results? So we propose three different approaches. The first one is very rudimentary, voting-based approach, in which we give equal weightage for every single metric, and then we do the voting and we decide which training regime is better. Second is domain-specific metric relevance. So in some situations, maximum calibration error, where we want to see the upper bound of the calibration error, might be needed. And in some cases, overconfidence error, which is OE, is required. So we can increase its relevance based on the domain, and then we use the voting based approach. So it will become a weightage voting based approach for model selection. The third one is margin for model selection. So if you focus on the last three plots here on the wide ResNet, there is a we see a very small gap between red and blue training regimes. Now, because the gap is so small, sometimes it's not right to incorporate them in the model selection process. So we say that there has to be a minimum margin for them to be used as a voting, used to be in a voting scheme. Otherwise, we'll discard them. So that becomes margin-based model selection. So earlier I showed you some of the results of the calibration on pre-trained as well as training regimes. Now we'll see what are different factors that affect the calibration. First is weight distribution. I wanted to see how the uh, calibration error is related to the standard deviation of the weight distribution of the neural network. So on the left, we have diabetic retinopathy dataset. On the right, we have histopathology dataset. The x-axis, we have calibration metrics. So because we have 6 calibration metrics, I have plotted in a single plot. So this x-axis is extended vertically. On the y-axis, we have standard deviation of the weight distribution of the neural network. Now this is a blob of self-supervised pre-trained model, SSLP, blue color. And these M, A, B, these are the initials of the metrics. So E for expected calibration error, M for maximum calibration error, A for ACE, B for Brad score, etc. There's another blob that is FSP. As we can see, the calibration error is very high. For SSLP, we see the calibration is very less. When the clusters are distinct, when their calibration error is far apart, we see there is a standard gap in the standard deviation of the weights. Whereas when the clusters are overlapping each other, basically when the calibration error very close to each other, we don't see the change or the gap in the standard deviation of the weights. The second factor we looked into when correlating the calibration is the learned representation. We wanted to see how learned representation gets affected when we see the change in the calibrations, calibration values. For that, we compared neural network representation from FSP and SSLP training regimes. We used central kernel alignment approach, which measures the similarity between the activation of hidden layers of a neural network. So let's suppose you have these many layers in a neural network, and we wanted to see how conv3 is related to every other layer in the neural network. So we have a 2D grid in that way. And higher the value, the brighter the number is, the brighter value, which means the higher similarity. And the lower the value means it's less similar. If we use CK plots for our research, and we have used FSP and SSLP, so these are the CK plots for FSP and SSLP training regimes. And for column wise, we have dataset sizes. What we see is that, let's suppose I just wanted to focus on FSP, the first row. The initial layers up to 120 for each dataset size are very similar. Same is the observation for SSLP. But as we move towards like last layers, like 120 to 140, the blocks which I've colored, we see that for FSP, the model representations, the learned representations, they become less similar. As you can see, these bands, the black bands represent less similarity. Whereas when we see this SSLP, the representations become very similar. And we call it redundancy in the learned representation. And because of this redundancy, it imparts implicit regularization in the model. Because of this regularization, it reduces overconfidence. Therefore, it improves the model calibration. And we have already seen in the previous plots that the SSLP calibration was far better than the FSP calibration. Just to summarize, we have compared the calibration and performance analysis on 3 different data sets, 4 different sizes, 3 architectures, and 3 training regimes. We observed that the transfer learning helps improve the performance over random initialized models. Self-supervised learning pre-trained is better calibrated than FSP, and the performance is also either better or on par with FSP. Dataset size has significant effect on the calibration performance, and we see that the larger the dataset size, the better is for the calibration. Increasing model capacity shows very minimal improvement, and the change in calibration can also be correlated with the change in the weights or the standard deviation of the weights, as well as the learned representations. The limitation or future work we can see here is that we can extend this work to 3D datasets and other SSL techniques like contrastive learning SSL or contrastive SSL or generative SSL. This work was published in Computer Methods and Program in Biomedicine. So if you want to read, there are a lot many interesting observation in the supplementary material where we have used RAD ImageNet pre-training, not just the ImageNet pre-training, as well as we have used rotation-based SSL task for or autoencoder based SSL task for comparison, and there are very interesting findings for them. Thank you for attending and thank you for being there. And if this research interests you, or if you would like to discuss your interesting problems, I'm open for collaborations. So feel free to just email me. Thank you.